Okay, so welcome to Math 409 problem solving. What I want to do is I want to do the egg drop problem today. Oh, it's not showing to me. Okay, so what I want to do is I want to do the egg drop problem today. Has anybody here seen this problem before? All right, so if you've seen the problem, you are unfortunately not allowed to play for the beginning of the class. You can play later, because I want to try to do a twist. So the way the problem works is this is an extremely unreasonable situation. But there's a lot of good mathematics behind this, and that's why I want to do this. So here you go. You have a building with n floors, and you have 2 eggs. And if you drop to some special value b, if you drop the egg from floor b or higher, it breaks. And by break, I mean it completely shatters. It is gone. You cannot use it again. If you drop it from any floor below b, there is no damage done to the egg. You can drop it as many times as you want, as long as you drop it from below B. But once you drop it from floor B or greater, the egg breaks. And your goal is to figure out what is B. Okay, so does everybody understand the problem? At this point, you should have no understanding of why we care about this. Yeah, this is not something that is going to happen to you in real life. But there's good math behind this. So we have a building, there's some special floor, we don't know where it is. And we want to figure it out, and we have 2 eggs. And I want to figure out what is your best strategy to determine B. So before we try to figure this out, I want you to tell me what are some questions or things we should be thinking about for this problem. So when you see this, what comes to mind? So when you see the word best or best strategy, what are you thinking of? What makes the strategy best? Okay, in what sense? Because there's lots of different metrics we can use for loss.
Consider a loss of broken egg.
Okay, loss is broken egg. So at the end of the day, we don't care how many eggs we are left with. We just care, can we figure out what that floor B is? There's no value to the eggs at the end of the day. If there were, then you might want to try to preserve some eggs while figuring out what the floor is. So we will assume the eggs are meaningless at the end of the day.
Are they meaningful in the sense that we need them to figure out?
Well, we need them to try to figure out and to come up with a strategy. But how will you determine if one strategy is better than another? Less number of drops. And what do you mean by less number of drops?
You can figure out. You can throw in like less.
All right, so maybe you want to minimize the number of drops. Well, let's say that in one strategy, all but once, it only takes 1 drop. And in 1 drop, which happens 1 in a million times, it takes 1,000,000 drops. Okay, so almost all the time it takes 1 drop, 1 out of 1,000,000, it takes 1,000,000 drops. About how many drops will it take on average? So 1 drop, 1 drop, 1 drop, 1 drop, 1 drop, 1 drop, and then 999,999, 1 drop, and then 1,000,000 drops. So if you add up, you've done 1,000,000 runs, 1,000,000 trials. How many drops was it? On average, it was. It's not 1. So let's do a little bit more slowly. So here, let's say strategy 1. Let's say for 999,999 cases, it is 1 drop. For 1 case, it is, let's make it 2,000,001 drops. So what is the average number in this situation? So average number of drops, well, in 999,999 out of 1 million, it was 1, right? And then in 1 out of 1 million, it was what? So if I've chosen those numbers correctly, what does this average to? So this would just be 3. So maybe in strategy 2, it's always 2 drops. So the average number of drops is going to be what? Jack, have you seen the egg drop problem before? So you have a building with n floors, you have 2 eggs. If you drop it from floor B or higher, they crack and can never be used. If you drop it from floor B -1 or lower, there's no damage and you can keep reusing it. And you want to try to figure out what is that special value of B? What is the floor where they break? Okay. So in this case, the average number of drops is what in the second case? 2. Which strategy is better, strategy 1 or strategy 2? You can defend either answer. So can somebody give me a reason why strategy 2 might be better?
Worst case runtime is lower.
The worst case runtime is lower. What's the average runtime in strategy 2? So what's the average runtime in strategy 2? It's just 2. What's the average runtime in strategy 1? It's 3. Very much. Okay. So should we always do strategy 2? Why might we want to do strategy 1?
Say if somehow you're just like given 1 egg and you just have to figure it out.
Well, no, I'm just saying it's not a function of how many eggs I have. I'm just saying when I use strategy 1, let's say 999,000 out of 999,999 cases will require just 1 drop. Somehow I'm able to figure out with just 1 drop. But there's this one annoying case, this one special choice of B that's going to cost me a little bit over 2 million drops to figure it out. Chances are you get it in 1. The odds that you are unlucky is 1 in a million. And so unless you're in that unlucky case, if you use strategy 1, you're going to get it in just 1 drop. Strategy 1 is faster most of the time. Why might we not want to do strategy 1 all the time? Well, because when strategy 1 fails, boy, does it fail. It's horrible. So if we do strategy 2 is the safest strategy. You'll always get it in 2. Strategy 1 is every now and then, once in a million, it's going to be horrible. So when you're trying to come up with what's your best strategy, you have to decide what you mean by best. Are you trying to minimize the expected number of drops? Or are you trying to minimize the worst case scenario? So frequently, we often minimize the worst case scenario. Okay, and that's a really easy thing to compute, is just say, if anything can go wrong with the luck that I'm having, it will. And so let's choose a strategy that minimizes my exposure to harm. And as somebody who taught a class on the pandemics, recently, thinking about worst case scenarios is not an unreasonable thing to be thinking about. Now, it is worth noting that sometimes a hybrid strategy is better. Can anybody think of a way to combine strategies 1 and 2 from before? So how could we combine strategies 1 and 2 to get something better?
So in case of the worst is to other cases.
Okay, and so how would we know when to use either?
You should be able to decide when is the worst.
But I'm saying, how do I know? Explicitly tell me, pretend I don't know anything, what I should do. I have strategy 1, strategy 2. You have to tell me which strategy to apply. So I should what?
But applying strategy 1 first. If it doesn't work, strategy 2.
Good. So I start with strategy 1. And how long do I go with strategy 1 before I give up on it and go to strategy 2?
Once.
Right. So if it hasn't finished after one time, then I shift to strategy 2. So the hybrid strategy is start with strategy 1. If work's done, else shift to strategy 2. And now, worst case, how many drops do you have? Worst case would be 3. So worst case is 3 drops. Average is only slightly above 1 drop. So this is the advantage of a hybrid strategy. And again, this is the general principle I want you to extract from this, is that we might be in a situation where we have choices of what we do. Stay with a certain choice for a while. You know, if this works most of the time really well, okay, I'll run with it for a while. And then if it's not doing well, I'll give up. The problem is you need to know when to give up. And for most of us in life, we don't necessarily know when to give up. If you've ever been waiting in a line and you start to get frustrated, should I move to another line? Or I've been put on hold, even though my call is very important to them. They've told me that multiple times. You know, they've put me on hold. Do I hang up and try again? Some systems are now nice, and when they put you on hold, they actually tell you, this is about how long you will be on hold, or you can actually leave your number and they'll call you back later. The last time I was on hold with American, we'll call you back sometime between 1 and 11 hours from now. So it was a long wait time, but you at least have that situation. Okay, so the problem we're doing is the egg drop problem. Have you seen this before? You have a building with n floors, you have 2 eggs, and if you drop the egg from floor B or higher for some special value of B, the eggs will break and never be usable again. If you drop them from B-1 or lower, there's no damage. And we want to figure out what is that value of B, and we want to protect ourselves against the worst case scenario. So for example, I don't know where that floor B is. You might say, maybe we know that there's a uniform distribution and all floors equally likely to be B. Or maybe it's a Gaussian distribution about 50. So if you have information like that, that might color how you choose to do things. So assume no matter what strategy you choose, I will choose the floor to be the worst possible value for whatever strategy you come up with. Okay? So does everybody understand the problem? All right. If it helps, I promised I would bring M&Ms from the M&Ms games. If anybody wants to, you're welcome to just either take some or pass them around. You can use these to model eggs, but I do not trust college students with throwing eggs in a classroom setting. Can anybody give me a strategy to try to solve this problem? Or tell me that maybe this isn't the problem we should be looking at initially. Maybe there's a different problem we should be looking at. So should we be trying to look at the problem of whatever? So anybody have any thoughts, either on this problem or on a related problem? I don't care if the strategy is good. I just want some strategy right now. So,
Dropping the first egg halfway.
okay, good. So we'll call it the halfway strategy. So first egg at n/2. Okay, what happens if it cracks?
Then
You've got one egg left. Now what do?
either start from the bottom or start at like n/4.
Well, once the second egg cracks, you have no more eggs.
Start at the bottom.
So you have to start at the bottom. So first egg at n/2, if cracks, then 1, 2, 3, ... like that. So what you're doing is by starting in the middle, if it doesn't crack, you've eliminated 50%. And if it doesn't crack at n/2, where would you go next? So it doesn't crack at the halfway point. So now you know it's somewhere between n/2 and n. So where would you do your next drop if the first egg doesn't break? Not n/2 plus 1.
3/4.
3/4. You did your halfway drop, right? And so if the first egg doesn't crack when you drop it halfway, then do half of this. So this over here was 1/2 n. So this over here would be basically 3/4 n.
I have a question.
Yes.
If it cracked at 1/2 end, and we only have one egg left,
Yep. Then you have to start off at the bottom and go up one at a time. You have no choice. There's nothing else you can do. Once it cracks, it's unavailable. So your strategy is a little bit risky, right? Because if it fails, then you're down to just one egg, and when you have only one egg, you have no choice. But if it doesn't break at n/2, you've eliminated 50%. So high risk, high reward.
can't you automatically eliminate 50% if you just went up like every 2?
Okay, so you are the opposite. You are the opposite, and I was hoping somebody would say this. So the two-timer. I realize that has connotations. It was deliberate. All right, so we'll do the two-timer strategy, where the first egg at 2, and now imagine your egg cracks at 2. You're golden, right? If the egg cracks at 2, what are the only possibilities for that key floor? 2 minus 1, also known as 1, or 2. So you have one egg left, and you can easily tell. If it doesn't crack at 2, then you would try 4, then 6, then 8. If crack, either 1 or 2. Not crack, try 4. Not crack, try 6. So your strategies are complete opposite. So your strategy, you eliminate a whole slew in the beginning if you're lucky. And if you're unlucky, then you've got to go one at a time. Your strategy, once your egg cracks, you basically know where it is. But if the bad floor is towards the top, you're going to have a lot of drops before you finally get that first egg to crack. So the question is, which strategy do you think is better? The halfway strategy or the two-timer strategy? So let's do a worst case scenario analysis.
I have a question.
Yes.
Do we lose if we break both of the eggs?
Yes. But only if you don't know what the floor B is. It's okay if both eggs are broken if you know what B is.
Could you do the same two-timer strategy for 3?
So you could do it every 3rd or every 4th, every 5th. So
I feel like if you did it every 3 though, and it broke on 3, then you could test on 2, and if it broke on 2, you'd know it was 1, and like so on.
So we'll call it do the every X.
Okay.
So if you do every X, once it breaks, then how many does it require?
Or X minus 1.
X minus 1, I think. And again, whenever you do algebra at the board, you're always off by up to like 1 in all these calculations. So I might be a little bit off in some places where maybe it's supposed to be -1 or something like that. So let's look at the extreme cases. For the halfway, what's the worst possible thing that could happen? It breaks on the first drop. So you had 1 and it broke. And then how many more could you have to do? I think it's n over 2 minus 1. Because if it broke on floor 50, you could have to do 49 more. So it'd be, I think, n halves minus 1, go floor by floor. And so this is basically n over 2. And I'm not going to worry about it, is n an even number or something like that. So in the halfway strategy, it's going to take us about n over 2 drops. Now let's do the 2-timer. Worst case scenario, how many drops would you have to do before you finally get your first crack? You could drop it at 2, 4, 6, 8. So how many drops would you have? Not n over 2 plus, no, just before the first egg breaks. The worst case would be is if your egg breaks on drop n over 2. So does everybody see it would be n over 2 before it breaks? And then once it breaks, how many more do you have? Plus 1.
But would we already know that if it broke on n over 2, that it would have to be n over 2 minus 1?
No, because it might be okay on floor n over 2 minus 1. So imagine it broke on floor 68. We know it was okay on 66. We know it's not okay on 68. So we don't know, is it 68 or 67? So it takes us 1 more drop. So it is n over 2 plus 1. So you just barely lose. So the halfway beats the 2-timer, but by the smallest possible margin in the worst case analysis.
Does the 3-timer take n over 3?
So now let's think, well, instead of the 3-timer, let's do the X-timer. It shifted to text, and when I use text now, it actually causes some issues. So let's do the X-timer. You do every X. So worst case scenario, how many times would you have to do it before you get to the top? N over X. And now, how many more do you have to do?
X minus 1.
X minus 1. And so in fact, what I want to do is I want to rewrite this 1. I'm going to rewrite this 1 as 2 minus 1. That's a better way of viewing 1. It's 2 minus 1. And so now, this is going to be n over x plus x minus 1. So we've looked at extreme values of x. We've looked at x equals 2, and we've looked at x equals n halves. Where did we look at x equals n? Okay. Yeah, right. Because I've got to view the one as n halves. Right. Okay. So the X-timer is n over x plus x minus 1. How can I figure out what the best choice of x is? So f of x is n over x plus x minus 1. How do I find the best value of x? Take the derivative. The minus 1 doesn't really matter. So f prime of x, n over x, that's going to become negative n over x squared plus 1. So the critical points are where f prime of x equals 0. So I need negative n over x squared equals 1. So x is equal to the square root of n. What are the extreme values of x? I'm sorry?
or positive.
Oh, sorry, yes, there's no longer the negative sign because I moved things up, thank you. So it's basically telling us that if we have a building with n floors, drop it every square root of n. What about the endpoints? It's not enough to find the critical points. What are the endpoints? X equals what?
And
1 or 2 and n. And clearly, if we do either one of those, we see n over x plus x is going to be much worse. So f of 1, f of 2, f of n are much larger than f of square root of n. And f of square root of n is basically going to be n divided by square root of n plus square root of n minus 1. So it's going to be basically 2 square roots of n minus 1. Now, you may not be happy with this because this is using calculus. I don't know how long it's been since you've used calculus.
After the boys' class in the fall of 1965.
Okay, so it's been a while. So can we do this without calculus? So who can look at the function n over x plus x minus 1 and try to solve this without calculus as to what the best value is? Minimize or close to it n over x plus x minus 1. Can you think of a way?
oh yeah, should we factor out the 1 over x? Then we have a quadratic polynomial that we can write as basically x minus square root of n squared.
But you still have to deal with that.
Oh yeah, but if we have a quadratic polynomial, basically a parabola, it's very easy to find the minimum of parabola.
So you'll be doing like a change of. You want to factor out the 1 over x?
And then we would have basically x squared plus an x minus 1.
Wait, but you have to multiply all those by 1 over x. And so you have a parabola, but it's a parabola times 1 over x. So let's think about what's going on.
Yes, that's right.
So there's a general principle here which I love. Now, of these 3 quantities, which quantity doesn't really matter when we're trying to minimize?
Minus 1.
The minus 1. That's always there. It's a fixed cost. So this is a fixed cost. Now, what is the n over x? The n over x is coming from going every x. The larger x is, the more savings. So this is smaller the larger x is, right? Because that means we're eliminating more floors when the egg doesn't crack. What about this case over here? This is larger the smaller x is. So we have 2 competing influences. The first term, x, we want x to be large, because if x is large, the first term becomes small. But the next term wants x to be small. So we have 2 competing influences. Now, we found the best choice to use by using calculus. If we don't want to use calculus, we can just approximate and say, look, I've got 2 competing influences. They're pulling me in different directions. What's one way to come up with a reasonable solution? So this makes x want to be large. This makes x want to be small. How do I harmonize them? What could I do?
Logarithm.
Not logarithm, not a bad idea though. I've got 2 competing influences. What could I do to balance them out? How could I find an x that balances them out? What equation would I look at? Yeah, n over x equals x. Make them equal. So consider n over x equals x. That implies n equals x squared, which amazingly gives us x equals square root of n. So if I just take the 2 competing forces and say, well, look, rather than using this advanced machinery from calculus, I've got 2 things pulling me in opposite directions. Let's just say they're both going to be equally bad. And I'll choose the value of x that does that. And it turns out that does a pretty good job. All right. Any questions with how to do the standard egg drop problem? So to some extent, doing this problem, we were implicitly doing something else first. And again, this is a big theme in problem solving, is you often are given a problem that you are asked to solve, but that's not necessarily what you should be solving, just because somebody says this is what they want. Any Star Trek Next Generation fans here by any chance? There was a nice scene when Scotty from the original Star Trek series comes forward 70 years in time and meets the crew of the new Enterprise. And he's making a pest of himself, and the new chief engineer just wants him to get out of his way so he can get his work done. And says, could you please, give me some space, I got to do this sensor study for the captain. Well, how long will it take? An hour. And how long did you tell the captain it would take? An hour. Laddie, you'll never get a reputation as a miracle worker. Captains are like little kids. They want everything and they want it now. Your job is to give them what they need. And so over here, just because somebody tells you, I want you to solve this problem, that's not necessarily the first thing you should be solving. So the problem I gave you initially was we are dropping an egg from a building with n, we're dropping 2 eggs from a building with n floors. We want to figure this out. How would you generalize this problem? So the problem I gave you is you have 2 eggs in a building with n floors. Find B. What's the general problem? You have a lot of eggs. You have some number of eggs. I'd love to say you have E eggs, but in a math class, E has connotations, and I cannot use E for the number of eggs. Okay, so more generally, let's consider K eggs, N floors. So case, let's do K equals 1. That's what we should have done first. When you have just 1 egg, what would you do? Yeah, you have no choice. No choice. Go 1, 2, 3, 4, ... Now do K equals 2. Basically, once the egg breaks, when you have 2 eggs, you reduce to the K equals 1 case. So once first egg breaks, now in the K equals 1 problem, do we have a strategy to handle 2 eggs? So what was our strategy? So where do we drop the first egg? So we did a square root drop. How might you do? Now, do we know that this is the best strategy? We just know that this was a candidate. So it turns out this is not the best strategy, because if the egg doesn't break, as soon as it doesn't break, we now have a smaller building. So note, if first egg doesn't break, now have 2 floors and n minus, 2 eggs and n minus x floors, right? So we wouldn't drop the next one necessarily another x units above. What you might want to do is you might want to have the initial drop a little bit large, because if the first one breaks, great, we'll go floor by floor by floor. When we had those 2 factors, when we had that n over x, the reason this was bad is if it took a lot of drops before that first egg broke. So maybe what we should do is the first drop should be a little bit more than the square root of n, and it gets smaller as we go down. Because if you do a little bit larger drop in the beginning, yes, then the next term here is going to be worse, but this term will be small. So for example, let's say n equals 100. And I think this roughly works. Let's do the first drop at 14? Nope. So I'm hoping that I'm remembering this properly. So if it breaks, how many drops do we need? If breaks, need how many more? 13 more. The total is 14. If the next drop, so if it didn't break on the first drop, then the next one we move up 13. If breaks need how many? How many? 12. So I'm trying to make the total always the same. And then if this hasn't broken, next at 12, if breaks need how many more? So I dropped the first one at 14, the next one, I'll write it this way. At 14 plus 13 is 27. And the next one would be 27 plus 12 is 39 in terms of what floor. Is I start my first drop at floor 14, the next drop at floor 27, the next drop at floor 39. If it now breaks, I just moved up 12 floors. So how many more drops is it going to take? 11. So the total is 14. So what I'm doing is in each scenario, I'm having it always take 14 drops. And so after 39, what would come next? It'd be 39 plus 11, right? Is 50. And then 50 plus 10 is 60. And then 60 plus 9 is 69. 69 plus 8 is 77. And I'll just continue over here. 77 plus 7 is 84. 84 plus 6 is 90. 90 plus 5 is 95. 95 plus 4 is 99. So I think what I really want is 105 floors. But this is enough to give a sense of what's going on. And so when you look at what's going on here, I'm able to do a little bit of a savings. How many drops is this? 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4. Well, if I go all the way down, worst case, you see it's going to be about 14 drops. 14 is less than 100 over the square root of 100 plus the square root of 100 minus 1, which is 19. So by extending it out a little bit, what we're essentially doing is we're using triangle numbers. And you look for the closest triangle number to your floor, and you can improve it by just a little bit. So I'm not going to go into too much detail on this. It's something that you can just think about. The naive strategy of doing every X is very simple to implement and discuss, but with a little bit of tweaking, you can do slightly better. Let's keep it to the pure strategy though, okay? So now you have 3 eggs. What do? What happens once one of the 3 eggs breaks?
You have the 2-egg problem.
You have the 2-egg problem. So with however many floors you have left, it's the 2-egg problem. So how would you figure out if you want to do every X, right? What's the worst case you could have for the 3-egg problem if you're doing it every X floors? Do every X till break. So how many times could we do it if we're doing every X? I'm sorry? Well, the building is n floors. I'm moving up every X. So how many drops, worst case scenario, before the first egg breaks? N over X. And now, once that first egg breaks, it's the 2-egg problem. With how many floors? With X floors. And we just showed a moment ago that if you have x floors, it's square root of x plus square root of x minus 1. So it's basically 2 square roots of x minus 1. Does everybody see where that comes from? This is coming from, in the 2-egg problem, it was, the best choice was x equals square root of n. So if you have n floors, it's n over root n plus root over n minus 1. It's 2 root n minus 1. So now we want to minimize this. So how do we minimize? What can we do? Give me 2 ways to minimize. One that will actually give the minimum and one that might give something close. Can somebody give me a method that doesn't use advanced mathematics that will get me close? Again, I've got 2 competing influences. I have the n over x and I have the 2 root x minus 1. So what could I do? Set them equal. So approximately n over x equals 2 square root of x. So n over 2 equals x to the 3 halves. So x is equal to n over 2 to the 2/3. If it's n over 2 to the 2/3, maybe I should view the square root of n as maybe n to the 1/2. If I had 4 eggs, what might you guess for the exponent? X to the n to the what?
3/4.
Maybe n to the 3/4. So we're beginning to even make conjectures. But we know calculus. So we have f of x equals n x to the minus 1 plus 2x to the 1/2 minus 1, right? So what's the derivative? It'll be negative n x to the negative 2. The 2 and the 1/2 cancel. That's nice. And we just get x to the negative 1/2, right? So the critical point, we want f prime of x to equal 0. Therefore, n over x squared equals 1 over the square root of x. So n equals x to the 3 halves. So x is equal to n to the 2/3. So this is a little bit better than just the naive having the 2 approach. We got the right order of magnitude. We got the right power of n. Both approaches gave n to the 2/3, but they gave slightly different constants. So, again, it's really simple to just say, look, I've got 2 bad terms. Let's set them equal to each other. It's not going to give you the best solution. This is why we develop things like calculus. But it will get you something that's pretty close. Okay, we've dropped 1 egg, at least theoretically. We've dropped 2 eggs, at least theoretically. We've dropped 3 eggs, at least theoretically. What should we do now?
What if you have an unlimited supply of eggs?
Well, but again, we don't care how many eggs we have left at the end. So what case should we look at next? We've done 1 egg, 2 eggs, 3 eggs. I'm sorry? No. No, I don't want to do an arbitrary number. What should we do next? 4. All right, we've got a few minutes left. Let's do 4 eggs. So now we have 4 eggs. So what strategy do we do? So 2 eggs, we dropped the eggs, and once 1 broke, we had the 2-egg problem. Now what will happen? And drop 1 and get the 3-egg problem. So it would be n over x, and now it's the 3 eggs with how many floors? We're doing it every x. Worst case is we have n over x times. So if it breaks, how many floors are there? X. It's really, I think, x minus 1, but I don't want to write x minus 1. So it's 3 eggs with x floors. Really, x minus 1, I know. I just have to write that because I'm posting the slides. All right, so with the 3-egg problem, we have to go back and say, well, okay, so we have x equals n to the 2/3. So if we plug that in, f of n to the 2/3 is going to be n divided by n to the 2/3, which is n to the 1/3, right? Plus 2 times n to the 2/3 to the 1/2, which is also n to the 1/3, minus 1, which is basically 2n to the 1/3. Right? I'm sorry? 3, sorry. I think, yeah, I can change the 2 to a 3. Yes, that's not too bad. Okay, so now if we come in over here, we're going to have 3n to the 1/3 minus 1. The 1 doesn't matter. Oh, I'm sorry, that n is an x. And so now I'll actually write a good 3. And so how would we figure out where this is minimized? What would we do? You know, lather, rinse, repeat, shampoo mathematics, right? What do we do? So one is set them equal, the other one's derivative. So if we do the derivative, we would get f prime of x is going to be negative n x to the minus 2. The 3 and the 1/3 cancel, that's nice. And we'll have x to the negative 2/3. So a critical point will get n over x squared equals x to the negative 2/3. Therefore, we get n equals, we bring that over, that'll become x to the 2 minus 2/3. That's 4/3. Therefore, x is equal to n to the 3/4. And so you should be able to now do the general case. And you should be able to prove that the exponent really will be eggs minus 1 divided by eggs. Unless, unless we ended in a local extreme. So what you said is when we had 3 eggs, keep dropping, and once an egg breaks, we're now in the 2-egg problem. When we have 4 eggs, we can drop, and once 1 egg breaks, we can then say we're in the 3-egg problem. Could we have adopted a different strategy for 4 eggs?
Yeah, well, if we have like a lot of it, we can just use binary search and get logarithmic complexity, which is better.
But you know, again, whatever, I mean, to some extent, I will choose it to be whatever's the worst case for you. But I do agree that the binary search is a good idea. So with the way we were doing 4 eggs, we said, let's keep going until that first egg cracks, and then we'll reduce to the 3-egg problem. How else could we have done it? What we were doing is we were viewing it as egg, and then egg, egg, egg. We viewed it like that. We had 2 sets. One set was 1 egg, and then as soon as that breaks, we then have 3 eggs. How else could we have viewed it? So we could have had egg, egg, and then egg, egg. Is knowing that we have 4 eggs, maybe it's better to have 2 eggs first, and I use those 2 eggs until both of those eggs break, and then I move to the 2 problem. So this all comes down to ways to group. So I have done it pretty well. I have timed it so it is exactly 10:50, class is over, and I have left it as a question for you to think about. So for Monday, tell me, is it better to view it as 2 sets of 2 eggs, or 1 egg and then 3 eggs? Or are they the same? All right, so this is a good place to stop. Have a great weekend. If anybody is interested or able to join us for coffee, we will be heading